Okay, so following the hint for this question, what two equations may apply? Well, we're talking about an orbit here, and the two new equations we've been working with are the orbital speed equation and a second equation that was kind of introduced works with the period for an orbit. The speed is distance over time in general. That's just a kinematics formula. But for an orbit that goes in a circle, the distance is the circumference, which is 2 pi r. And the time is called the period, the time to make one orbit. So those are actually the two equations that both contain v and r in them. Those are two unknowns, so I can solve for those two. I know the value of everything else, so I can solve for the two missing things. Okay, so I'm going to do some rearranging here. First of all, if I call these equations 1 and 2, I notice that they're both isolated for v, so that makes it an easy substitution. I can just sub one into the other, or another way we say it is we set them equal to each other. They're both equal to v, so they should both be equal to the same thing. So I'll set them equal to each other. So that is root gm over r is going to have to equal 2 pi r over the period. And then I can solve for the radius. How do you go about isolating this for radius? I mean, you just use your regular algebra skills. What you do to one side, you do to the other side. And I'm going to start by squaring both sides because I don't really like that square root on the left side. So I'll square both sides. So 2 squared is 4, pi squared is pi squared. And then square the radius and square the period. Okay, then to solve for r, I've got r on both sides here. So I think a good cross multiplication will be effective here. So cross multiply, it'll be gmt, and it'll be 4 pi squared r cubed. Here, r squared times r is r cubed. From here, divide both sides by 4 pi squared. And then from here, cube root both sides, cube root both sides. And I think that'll do it. Okay, so now I'm ready to fill in the values here. These are, I'm gonna need a ton of space here because a lot of these are in scientific notation. The period is 24 hours, but I'm gonna need that in SI units in seconds. So 24 hours times 60 minutes in an hour times 60 seconds in a minute. So 86,400 seconds. Okay, so now I'll try to fill them in. So cube root g, so 6.67 times 10 to the negative 11 times the mass of the Earth, so 5.972 times 10 to the 24 times my period. There's a mistake. The period needs to be squared. So I'm going to backtrack here. If I go, let's make this correction here. So if I start, this is my initial step, and to go to this step, I squared both sides. and it looks like I forgot to square the period. I squared everything else, but I forgot to square the period. It's a good thing I caught that now. So I'll just carry that through this whole thing. And that's one advantage of saving the substitution till the very end. If you did make a mistake, at least you did not sub in all these values and then have to change them all. All right, calculator time. Okay, so I'm getting 4.2, 3 sig figs here, 4.22 times 10 to the exponent 7 meters. So that would be the radius of the orbit. And I'm just going to take a second to go on Google here, and I'm going to search up radius of geosynchronous orbit. And it is giving me 42,164 kilometers. Convert that to meters, and you would get really close to what I got here. So let me say Google geosynchronous satellite radius. It's giving me 4.2164 times 10 to the 7. Okay, so not exactly quite what we calculated. Pretty close. So these significant digits, they kind of matter. Well, this is what I got. Yeah, because this rounds to 4.22 times 10 to the 7. Okay, so significant digits wise, we got the same thing as Google is saying. And now the speed. We want to solve for the speed as well. So since we have our answer to r, we can go back and use it in any one of our original equations. We have a choice of 2. So it looks like the second equation will be a bit easier. So, so going back to equation 2, speed equals 2 pi r over t. That'll equal to 2 times pi times the answer I just got. Divided by the period, 86,400 seconds. Yeah, I'll put the units in meters and seconds. Going to give me an answer in meters per second. Okay, coming up with 3,071, so I'll say 3.07 times 10 cubed meters per second. About 3,000 meters per second, roughly speaking. I guess might as well just Google that as well. So I'll Google speed of geosynchronous satellite. Oh, it's giving me miles per hour. Okay, it's giving me about 7,000 miles per hour. So let me go 7,000 miles per hour, 2 meters per second. And it's giving me 3, so Google is giving me 3,129 meters per second, which is still, to 2 sig figs, it's still 3.1 times 10 cubed. Or to 2 sig figs, sorry, it's still 3.1 times 10 cubed meters per second. All right, there you go, a geosynchronous satellite. All satellites that are geosynchronous have to go at this speed, and they have to be placed in an orbit with this specific radius. It's the only way it'll work. Not all satellites have to be geosynchronous, but the ones that we want to be geosynchronous, these have to be the properties.